dy dt, that's a terrible y, times the first one, x. And then I take a look. I'm trying to solve for dA dt. Good, I've got it. dx dt, do I know that? Yes, it's 8. Do I know y at the instant in time? Yes, it's 10. dy dt, do I know it? Yes. X? Yes. So I've got everything I need. I can solve for dA dt. I'll do it right here. dA dt is equal to dx dt, which was 8, times y, which is 10, plus dy dt, which is 3, times x, which was 20. And again, notice I'm not using my units. I'll get my units at the very end. So dA dt should be 8 times 10, it's 80 plus 60, 140, 140. And then it should be area, measurement of area over time. Area is squared units. I'm working with centimeters, so this should be centimeters squared per, because division here, time unit here was seconds, so centimeters per second. And that's it. I wanted to show you real quick, had I instead tried, shoot, I just erased what I needed to show you. Let's say I write down this equation, okay? But I write it down with the units, just to show you how it would work. It would have been dx dt, which was 8, I'm going to write it like this, centimeters per second, so that's like per 1 second, you could say, times y. Y was 10, but 10 centimeters, so 10 centimeters over 1, and then plus dy dt, which was 3 centimeters per 1 second, right? I erased it, but it said 3 centimeters per second, and then times x, and x was 20 centimeters, so I'm going to write 20 centimeters over 1. So I just wrote them like fractions so that you can see that when you put this together, you multiply across the top here, you get 80 centimeters squared over second, 1 second, plus 60 centimeters squared over 1 second. These have the same denominator, so this becomes 140 centimeters squared over 1 second, or I can just say per second. So it's the same answer, but just different way of doing it. I think this is useful. I mean, it's not bad, but here, I guess in this class, we can always determine the unit pretty easily by just looking at these two things. All right, number what? Next. Number 5. A cylindrical tank with a radius of 5 is being filled with water at a rate of 3 cubic meters per minute. Now, when we see cubic meters, we need to be thinking volume. How fast is the height of the water increasing? So, let me try and draw a general picture. General picture, we have a tank, cylindrical tank. It has a radius of 5 meters. That's fixed the whole time. And it's being filled with water, right? So we've got water being poured in here. Here's water being poured in. And the water level is somewhere in here, and the water level is going up, right? Because the water is going in, okay? So they tell us how fast the water is going in, and I'm going to write that down right now, what I know. I know that the volume, right, is increasing at a rate of 3 cubic meters per minute. So that is the change in volume with respect to time is 3 cubic meters every 1 minute. So when we see cubic meters per minute, that's a rate. So we know it's a derivative, and because it's cubic units, it's volume. So we have to kind of interpret that from the wording. So we know that. What we want to know is how fast the water level is rising. So the water level is actually the measurement from the bottom of the tank up, which I haven't labeled yet. And I think what I'll do is I'll label it H for height. You could use any letter there, but that makes sense to put H. So I want to know how fast H is increasing. I want to know the rate, so it's a derivative, the rate at which H is increasing. But the thing is, it doesn't tell me in the problem when to look. Okay? It doesn't say like at a specific moment. So the instant in time for this problem, there is none, not applicable. Because if we pour water in at a constant rate, and this is a cylindrical tank, this should just come up at a constant rate also. It doesn't matter where I am on the tank, it's still going to come up at the same rate. Compare that to a problem like this, where if we had a conical tank and we had the water going in, then that would be different. It would go up faster in the beginning, and then it would slow down as time went on, as we, I'm sure, talked about in class. So we don't have this instant in time, so when we say we want dH dt, we don't have anything to say like at a particular moment. So we're just going to keep working. What I want to do now is try and come up with an equation that relates this and this. So how is the volume of a cylindrical tank related to its height? Or sorry, how is the volume of a cylinder related to its height? So I'm talking about the volume of this piece right here, not the volume of the whole tank. So what's the volume of that blue piece? Well, if you look in your book, you'll find that the volume of a cylinder is pi r squared h. That's the volume of a cylinder. In this problem, though, the radius is always 5, right? That never changes ever, ever, this radius. So I can, at this point, replace this radius right here with 5 and square it and get 25. And I'm allowed to do that before I take the derivative, but only because it's constant throughout the entire problem. So that's the equation I'm going to differentiate. I'm going to differentiate with respect to time. Derivative of the left side is dv dt, which is what I am given, right? I was given this. And then over here, 25 pi is a constant, so I'm just going to write it down. And then times the derivative of h with respect to time, which is dH dt. dH dt is what I'm trying to find. So you can see here, here's what I want to know, and this is what I was given. So I should just be able to plug in 3 here. And then divide both sides by 25 pi. So dH dt should be 3 over 25 pi. And then what are my units? Well, height should be this height, and we're measuring everything in meters, so it should be meters per, and then my time measurement in this problem is minutes. So meters per minute. That's it. I'm not going to get a decimal, I'm just going to leave it. All right, let's look at number 6. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So we have a sphere. Here's my general picture. Has a radius. That radius is increasing. That's what it says. Tells me that that radius is increasing at a certain rate. So I'm going to write that down over here. I know, or I'm sorry, I'm given. I don't know, have I, I do this different ways sometimes, I apologize. We write down what we're given and what we want, okay? Or what we know and what we want. I'm given that the radius is increasing at a rate of 4 millimeters per second. Okay. How fast is the volume increasing? How fast is the rate? I want to know how fast, right, the volume is increasing at exactly the moment that the diameter I'll put capital D, equals 80 millimeters. So now that can help me draw my instant in time. At the instant in time I'm talking about, this sphere has a fixed radius of 80 millimeters. All right, so I'm going to try and come up with my formula now that's going to relate the volume of a sphere to its radius. The volume to its radius. So you can look it up in the book also. Its volume equals 4/3 pi r squared. That's the volume of a sphere. 4/3 pi r cubed. I don't know why I said that. 4/3 pi r cubed. And that's it. We have V and we have R in there, which is good, because we have V and we have R here. So notice I'm not going to fix my radius at anything yet. I'm going to take derivative because the radius is changing. So I take my derivative on the left, dv dt. Over here, 4/3 pi is a constant, so it's just going to come along for the ride. The derivative of something cubed is going to be 3 times that something squared, but then times the base, which is dr dt. And I can clean up, these 3's cancel. I get dv dt equals 4 pi times r squared times dr dt. And that's what I'm going to work with. dv dt is what I'm looking for. dr dt I'm given. But then I also need r. I need the radius at the instant in time. Oh, shoot. I accidentally wrote that. I'm sorry, that was diameter. Diameter straight across. Okay, let me fix that. The diameter straight across was 80. I want the radius. The radius obviously is half the diameter, so the radius is equal to 40 millimeters. So the only thing that was wrong there is my picture. So that's just one little tweak in the problem you got to pay attention to. They give you diameter, not radius. So when you come in here, you need to convert that diameter to the radius before you can plug it in. So let's plug in. If we plug in, we're looking at dv dt should be equal to 4 pi times 40 squared, not 80, times dr dt, which was 4. And if you do this, you get 25,600. And then my units will be the measurement of volume, which is whatever the unit is cubed. So it's going to be millimeters cubed, cubic millimeters, over time unit, which is seconds. And that's it. That's the rate at which the volume is increasing at exactly the moment the diameter is 80 millimeters. Number 8. These are going a little quicker than I thought. Probably too quick for you, your opinion, right? Instead, I'm probably moving a little too fast. I apologize. All right, this problem is different. All right, it says, suppose you were given an equation, 4x squared plus 9y squared equals 36. So this is a curve, all right? If we draw it, it's a curve. And part A, it says that x and y are functions of time. So as you draw the curve, right? Imagine a clock running in the background, and you have some way of drawing it, right? And they're telling you a little bit about how you're drawing it. It says, for part A, suppose that dy dt is 1/3. So the rate at which y changes is constant. It's 1/3. So the y coordinate is always changing at a certain rate as you draw it. it says for us to find dx dt, at the moment that x is 2, at the moment x is 2, and y equals 2/3 root 5. Okay, that's part A. So what I need to do is somehow figure out dx dt. So I'm going to need to have some equation that has x in it, and I need to have also an equation that has y in it so I can relate those together. And the equation I'm going to use, obviously, is the equation that's given because I'm working on that curve. So I'm going to take that equation. See, I'm not drawing, I don't have any pictures really I need to draw here. I mean, I could draw the curve, but I don't really need it. I'm going to take the derivative of this whole thing with respect to time. So the derivative of 4x squared with respect to time will be 8x times, so I just did power rule, 2 came out, replace it with a 1, and now I take derivative of x with respect to time, which is dx dt, plus, now I take derivative of 9y squared, so the 2 pops out, we get 18y to the first power, times the derivative of y itself, right, which would be dy dt, and then equals the derivative of the right side, which is 0. And notice that in this new formula, this new equation, dx dt is in there, dy dt is in there, I know what that is, x and y are also in there, and I know what those are. So I should be able to solve for this. So I'm just going to rewrite it, 8, now x is what? 2, so 8 times 2 times dx dt, plus 18 times y, that's a weird one, 2/3 root 5, times dy dt, which was 1/3. That must equal 0. So let's try and clean this up. Let's see. This is 3 goes into here 6 times, but then 3 goes into that twice. So we should just have 4 root 5 here. And then in front of it, we should have 16 dx dt equals 0. I'm trying to solve for this, so I'll move that to this side. 16 times dx dt equals negative 4 root 5. And then divide both sides by 16. And that reduces, so you get dx dt, that's a t, sorry, equals negative root 5 over 4. And that's it. That's what dx dt is. So if you draw this curve in such a way that the y, as you draw it, the y coordinate is always changing at a rate of 1/3, and maybe it's 1/3 centimeters per second or feet per second, whatever it is, just that's the rate, 1/3. Then at the moment you get to this point, this x and y coordinate, your x coordinate must be changing, okay? The left and right must be changing at that rate, negative root 5 over 4. So you're actually going to be coming, as you're drawing it, down to the left. I mean, sorry, to the left. At that point, you're drawing to the left a little bit. All right. Part B, I think I'm going to leave part B to you because what they do is they switch it around. They give you some information about dx dt. They want to know dy dt, and they give you a different point. And then you just go through the same thing. So I'll let you enjoy that yourself. But the answer you should get on part B, oh man, I didn't finish solving it. Oh well, you can figure it out. I thought I'd finished. All right. I started doing all the problems on paper before I did the video because I was like, well, just to be sure that I make sure I get everything right. And then I got to number 8, part B, and I was like, okay, I'm done. I'm just going to go make a video. So starting now, I have not worked these out. I can't remember the last time I worked these out. So if a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute,